Hello, Honors Pre-Calc BC. Today we are going to be talking about differentiability. Basically, differentiability is referring to whether you can take a derivative or not at a specific location. So if you can take a derivative or find the slope at a specific point, we say a function is differentiable at that x value. And if we cannot take the derivative at that specific point, then we say that the function is not differentiable at that location. So basically, a graph does not have a derivative of a point if the limit as x approaches a of f of x minus f of a all over x minus a does not exist. So there are several instances graphically where the derivative does not exist, and we're actually going to start to classify those today. So the first situation, which we've seen most frequently, is called a corner. A corner is where the one-sided derivatives are different. So probably the big situation in which we've seen that is with an absolute value graph. All right, so if you have the equation y equals the absolute value of x, you know that you have a vertex at 0, 0, and in this situation, to the right of 0, or greater than 0, the slope is 1. And when x is less than 0, your slope is negative 1. So this is a situation in which your left-hand derivative and your right-hand derivative are different. Left-hand derivative is negative 1, right-hand derivative is 1. We say, therefore, we are not differentiable at x equals 0, and that's because we have a corner. Okay, corners are always going to look like this. All right, so a couple other situations. Next, we have what is called a cusp. A cusp is a little bit different from a corner. The slope of the secant line approaches infinity from one side and negative infinity from the other. So here is an example. You can see visually it is different from a corner, right? The corner, you have a constant slope on this side and a constant slope on the other side. Here you can see that it gets steeper as you go, and so as you're approaching, in this case, 0, on the one side, you're getting steeper and steeper in the negative direction. So derivative approaching negative infinity. And on the other side, you're getting steeper and steeper in the positive direction, so approaching positive infinity. An example of an equation like this would be y equals x to the 2/3. Okay, so if you go ahead and, oh, this is 2/5. If you go ahead and graph this, that's what it looks like. Okay, you can see it is getting steeper as we go towards x equals 0. So we would not be differentiable at x equals 0. At x equals 0, and we call this a cusp. Periodically, you are going to be able to use your calculator and just say, hey, you have a cusp or you have a corner. And sometimes you're going to have to prove it with your derivatives. So we will be doing both. Okay. For now, I'm just telling you what the different ways to determine if something is not differentiable are. All right, number 3, vertical tangent. This is similar to what we're saying with cusp, only with a cusp, your slope approaches infinity from one side and negative infinity from the other. For a vertical tangent, you can approach infinity or negative infinity, but your slopes are going to be the same from both sides. So an example of that equation, one that has a vertical tangent, might be something like y equals the cube root of x. Okay, I'm just giving you some examples so you can see what these look like. So that would be x to the 1/3 power. So visually, you can see it looks pretty different. Okay, something like that. So as you approach 0 here, I didn't draw this very well, but you're getting steeper and steeper in the positive direction from one side. You're getting steeper and steeper from the positive direction, or in the positive direction on the other side. Since they're both approaching positive infinity, we say that it is not differentiable at x equals 0 due to what's called a vertical tangent. All right, and finally, a discontinuity. The function not continuous due to a jump, vertical asymptote, or hole. So we know this is an infinite discontinuity, and this is a removable discontinuity. If any of those situations occur, you also cannot take the derivative at that point. Okay, so just like we've been talking about, a function does need to be continuous in order for you to find the slope at that location, meaning the derivative. All right, fantastic. So those are the 4 situations you need to look out for to determine if you cannot take the derivative at a specific location. Personally, I would always check for continuity first, because if the function is not continuous, then we can't find the derivative immediately. Okay, so you can save yourself some trouble. All right, one more thing, local linearity. This is just an expression that says if you are differentiable at a point, zooming in really close to that point with your calculator will look like a line. So to give you an idea of what I mean here, if I just graph x squared, this is not considered a corner. And reason being, your slope is going to gradually shift from negative to 0 to positive, as opposed to over here, where it is a dramatic shift. Okay, so that's one reason that x squared, you will be able to find the derivative at this point. If you're not sure, you can zoom in. Let me show you this local linearity. So you can already kind of see it right down there. Zoom in. So I'm zooming in on the vertex. And sure enough, see how it's becoming like a straight line? Okay, so that means we can take the derivative at that point. If I try this with absolute value of x, where did it go? I can zoom in. I can zoom in. And you're going to notice that really nothing is happening. Okay, at that vertex, it is an immediate shift from your left hand slope to your right hand slope. Okay, so that's what a corner looks like, which means we cannot take the derivative at that location. Okay, one more thing before we try an example. If a function has a derivative at x equals a, okay, so if you can find the slope at a specific x value, then automatically it's also going to be continuous. Okay, so if you can find the derivative, it must be continuous. We say that differentiability implies continuity. So being able to find the derivative does mean the function is continuous. However, this is not true the other way around. Just because a function is continuous does not mean it is differentiable. Okay, so this absolute value graph right here, it's continuous. The limit, left-hand limit and right-hand limit, are the same all the way across. There are no holes, there are no jumps, there's no vertical asymptotes of any kind. However, we still can't take the derivative at x equals 0. Okay, because your slopes from the left and the right are not the same. So it being continuous doesn't necessarily mean you can find the derivative at every single point. Okay. So again, differentiability implies continuity, but continuity does not imply differentiability. This is an important topic that we can rediscuss on Monday. Okay. All right, so let's give this a try. Find all points in the domain of f of x equals the absolute value of x minus 2 plus 3, where f is not differentiable. Identify the problem as a cusp, corner, vertical tangent, or discontinuity. All right, well, this is an absolute value graph. It's definitely continuous. And we can just kind of draw a picture of this. You should know that your vertex is at 2, 3. And you have a positive in front, so it's going to be going up. Okay, and you should also know, just looking at this equation, what your slopes are. This side right here is going to have a slope of +1. This side right here is going to have a slope of -1. All right, so immediately we see we have an issue here. Your one-sided derivatives are different. Your left-hand derivative is a -1, and your right-hand derivative is a 1. And that means that at the point 2, 3, you have a corner. So we are not differentiable. At 2, 3, and that's due to a corner. And reason being, the left-hand derivative is not equal to the right-hand derivative. Okay, so this is just your explanation as to why it's specifically a corner. Now, what you could do is you could write this equation as a piecewise and then use your difference quotient, okay, or your alternate definition of derivative. That seems like a long time, or would take a long time, but let me show you how you would set it up. Your yellow portion right here, the one with the positive slope, that would be the equation x minus 2 plus 3, which is just x minus 1, or x plus 1, sorry. And that's when x is greater than 2, right? So that's the yellow portion. You could put the equal to there as well. Remember, you just need to have it somewhere. And then your negative slope, your blue line, would be negative x minus 2 plus 3. So that would be negative x plus 5, where x is less than 2. All right, so again, you can tell from this right away, oh, these two are linear. So your right-hand derivative is going to be a 1, and your left-hand derivative is going to be a -1. But you could do difference quotient if you want, or again, definition of derivative. I just want to show you how to do that for one of these in case you are interested. If you are not, you can just plow right ahead in this video. Okay, but I'll do it for this guy right here. So I'm going to do the limit as x approaches 2 from the right, and from the right I have the equation x plus 1. Okay, so this is, we'll write this out first, f of x minus f of a all over x minus a. So f of x is x plus 1 minus f of a is f of 2. It's what we get when we plug 2 in here. All over x minus a. So x minus 2. Again, this is not necessary. I just want to show you that it does work. Okay. And lo and behold, you get an x minus 2 over x minus 2, which does cancel, leaving you with the limit as x approaches 2 from the right of 1, which is just 1, which is the slope that we got. Okay, so I would not recommend wasting your time doing the alternate definition of derivative or the difference quotient. When you have a linear equation, you can just say what the slope is. All right, we have 2 more examples. Prove that f of x equals x to the 2/5 is not differentiable at x equals 0 using right and left-hand derivatives. State that the problem is at that point. So we're going to do this non-calculator. If it's a calculator portion, you type it on in and you look at it and you say what it is. Okay, but if it's non-calculator, we're going to have to use left and right-hand derivatives. Okay, so again, my alternate definition of derivative, which we talked about the other day, looks like this. And it doesn't really matter which one you use. What's nice about this one is that the purpose of it is used for at a specific point. But if you want to use the original definition of derivative, your original difference quotient, that's fine as well. Okay, I'm going to use this guy. So I'm approaching 0, and I'm going to start with 0 from the left of f of x minus f of a. Well, a is 0 all over x minus a. All right, well, that's nice because it's just x to the 2/5 over x. So now we're just going to go ahead and use our laws of exponents. And this is like a 5/5 down here. 5/5 minus 2/5 is 3/5 on the bottom. All right, so now here is the basic idea. We cannot plug a 0 in for x because then you'll have an undefined. So since we're approaching 0 from the left, you can think of this as you're plugging in like a negative 0.05, okay? Something really, really small or really, really close to 0 in the negative direction. Okay, so essentially you're doing 1 divided by a really small negative number. Okay, so when you do that, when you do 1 divided by a really small number, what's going to happen to that number? Well, it's going to approach an infinity. Okay, it gets bigger and bigger and bigger. Specifically, it's going to approach negative infinity. Okay, because you're going to plug in a negative number for x and you're going to cube it. So it's still going to be negative. Okay. So again, when you divide anything by a really small number, it's going to get bigger and bigger and bigger. Look. Okay, like if you do 1 divided by negative 0.000005. Okay, it's getting big. Big in the negative direction. Okay, all right, so there's that one. All right, so next we need to do this as x approaches 0 from the right. So you're going to notice that all of this work is going to be exactly the same. In fact, you can just come down to this right here because you're not a 0 from the right, like that's not going to change any of the work you do. So it's still this, but now you are plugging in a very small positive number, so like a 0.005. You're still doing 1 divided by a really small number, but it's going to be a positive number this time, so we will be approaching infinity. Okay, so notice you're approaching negative infinity from one direction and positive infinity from the other. That means you are dealing with a cusp. Okay, so we have a cusp at x equals 0, specifically at 0, 0, right? Because your x value is 0, and when you plug it in, you get a 0 as well. Because 1 secant goes to infinity, and the other goes to negative infinity. Okay? All right. Finally, determine where the graph is differentiable, continuous but not differentiable, neither continuous nor differentiable. So differentiable means where you can take the derivative. Okay? We can take the derivative anywhere where one of these things is not occurring. So we can't take the derivative at a corner, at a cusp, at a vertical tangent, or any other discontinuity. Okay, or excuse me, any discontinuity. So any of these locations, if they occur on our graph, it is not differentiable at that point. Okay, so let's look for those situations. You should notice that you have a discontinuity occurring at -2. You also have a discontinuity occurring at -3, and there's also a corner at x equals 0. So this is differentiable over all x's, or all reals, except at x equals -3, x equals -2, and x equals 0. X equals -3 is a whole or a removable discontinuity. X equals -2 is a jump discontinuity. And x equals 0 is a corner. All right, so that's where you can't take the derivative, those 3 locations. Now we're going to say where we're continuous, but not differentiable. Okay, so again, continuous, it's like a smooth curve. Okay, it's not a hole, it's not a jump. So it's continuous everywhere, but not differentiable at this guy right here, x equals 0. Okay, so it is still continuous at x equals 0, it's just not differentiable there. Okay, these other 2 locations, they're not continuous. Okay, remember discontinuity. Okay, and finally, where are we neither continuous nor differentiable? Okay, so it's not continuous, it's not differentiable either. Those are your other 2 locations. So we are not continuous or nor, I don't know which one it is. Okay, so neither continuous or differentiable at x equals -3 and x equals -2. All right, so remember, Monday we will be going over any questions that you have. All right, there is one more lesson I need to teach you. That will be taught on Tuesday, PSAT on Wednesday, workday Thursday, quiz on Friday. All right, go ahead, get started working on homework. Have a great day and a great weekend.